Hey everybody, today we're going to finish up this chapter on congruent triangles. Now, if you look at this particular note sheet, it says we need to get out protractors and rulers. We're not going to do that right this second. I want to make sure we have time to actually get through everything we need to get through. So I'm probably just going to spoil it for you, but that's okay. So I want you to notice something about these triangles here. So I want you to look at this angle. We're going to call that angle A. So we're going to label this, this first triangle ABC. And we're going to label this second triangle DEF. Now, hopefully you notice right off the bat, these two triangles are definitely not congruent. There's nothing about them that is congruent. I mean, we have a few congruent parts, but as far as like overall, if you look at them, obviously one is a lot bigger than the other one. They're not congruent. So, I said get your protractor out. We're not going to do that. I'm just going to spoil it. It turns out the measure of angle A is about 27 degrees, give or take a degree or so. I measured it out myself just to test it out. Now, on your paper, you should find out that the distance from A to B is about 3 inches. Now, again, if you don't have a ruler out, not a big deal. I just want to make sure we get through this. Okay, so this was about 27 degrees. This was about 3 inches. And then B to C, it turns out, was about 2 inches. Now, if you look, it turns out all of those same things happen to be true about triangle DEF, which is just so weird. You think to yourself, well, these two triangles aren't alike at all. It turns out the measure of angle D is also 27 degrees. The distance from D to E, also 3 inches. And the distance from E to F is also 2 inches. So, so it matches here. It matches here. And then it matches here. And so people have been asking, so why is it that angle side side doesn't work? Well, that's why. These two triangles have the exact same angle, the exact same side, and another side. So we have a matching angle side side here, but it is not proof that the two triangles are congruent. Now, we're going to put SSA here instead of ASS because we don't want that on our note sheet. That is not a valid way to prove triangles are congruent. So when we think about our list, we think about side, 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 angle, side, and angle, angle, side. And then we learned about the ones that don't work, and we talked about why they don't work. And you're going to eventually learn, when you get into trig class, that the reason it doesn't work is actually because of this angle right here. What you get when you are working through and you do your pre-calculus life or your trigonometry life later on, you learn that when you go opposite of that first side, you could end up getting an obtuse angle or an acute angle. Notice how in the picture, as soon as we went over to C there, we ended up with an obtuse angle. But when we went over to F, that one was acute. So they matched for a while. They were matching here, they were matching here, they were matching here. But as soon as we went across and we started looking at angles C and F, you start realizing, oh, wait a second, we have one of them that's acute, one of them that's obtuse. So it doesn't work. They don't match. Now, the question then becomes, what would happen if we knew that that angle wasn't going to be acute or obtuse? Then would we be allowed to use the theorem? So what would happen if we knew the angle wasn't going to be acute or obtuse? Well, when we're dealing with triangles, there's only three options. It's either acute or obtuse, or it's right. And that's what we're going to talk about here. We're going to learn a new theorem here, and it's going to actually sound very different than the others because it's going to be the hypotenuse leg theorem, otherwise known as the HL theorem. So here's how it looks. If the hypotenuse and a leg of one right triangle are congruent to the hypotenuse and a leg of another, they are congruent. So if we have a matching hypotenuse and we have a matching leg, then they are congruent triangles. We'll just sneak the word, let's add the word triangles in there. Just sounds better. There you go. Trying to cut it down so you'd be able to fit it on 2 lines. We'll just go with that. All right. I want to show you what this would actually look like in a proof. So it turns out these 2 triangles are congruent to each other. We need to prove it. Okay? Now, an HL theorem proof is going to look a little bit different than what we're used to for a couple of different reasons here. You're going to notice a couple of statements, 2 in particular that I can think of, that may end up looking a little bit differently than what you're used to. So let's put our statements over here. Okay, let's put our reasons over here. Now, when it comes time to do the given parts, you could do it either as one big statement and say given, or you could break them up into 2 separate statements and write given twice. I don't really care. It makes no difference whatsoever to me. So I'll do it as 2. Some people like that because it makes them feel good. Like, hey, now I've already done 2 steps. That's great. Now, AC is perpendicular to BD. Now, what do we know about perpendicular lines? We know that they make right angles. We're going to use that later. We also know that AB is congruent to AD because it was given. So we're going to put some marks right there and right there. Now, what else could we use? Well, if you look, we have a shared side. So what we could do here is we could say that side AC is congruent to side AC. Okay, now if we want to make this look pretty, we're going to have to put the lines over it, and we are going to have to do the congruent symbol. That was weird that it didn't come up earlier, but that's okay. Now, hopefully you know by now, we've been using that a bunch. It's called the reflexive property. So now we have a matching hypotenuse. Remember, that's a word we can use in right triangles. The longest side of the right triangle is called a hypotenuse. They match. We also have a matching leg. That was the one that we just marked with the reflexive property. A right triangle has a hypotenuse, and then a right triangle has 2 legs. As long as you can get one of each to match, then you know you're good. Now here's where it gets a little bit choppy, and this is where people are going to struggle with this proof. The next thing I want you to do is say something about the right angles. So in this case, what I'm going to have you say here is angle ACB and angle ACD, and I'm going to extend it all the way over here, are right angles. Hopefully you're writing a little bit smaller. I'm just going to try to get this all on one screen, so I'm going to do it this way. You can do whatever you need to do to make sure you're successful. All right. How do I know that they're right angles? Well, if you look at what was given, it didn't say that they were right angles, but it did say that AC was perpendicular to BD. So we're going to say definition of perpendicular. Now again, we're kind of running out of room here, so we'll just get creative. Yeah, close enough. Hopefully your paper looks better than this, but we're doing the best we can. Now, the next statement is a pain. I am not going to lie. It is a total pain, and you're going to think that you don't even need to do it because it seems repetitive. If angle ACB and ACD are right angles, then what that means is triangle ACB and triangle ACD are right triangles. It seems repetitive. Well, of course we knew they were we knew they were right triangles. They had right angles. You need to put it anyway. And here's the reason. In order to use the HL theorem, you need to have three things checked off. They need to have a hypotenuse, they need to have a leg, and then they need to be right triangles. If they are not right triangles, if you don't say something about that, then you can't use the HL theorem. So if you're wondering what do kids get wrong the most, I'll tell you right now, it's definitely that, without a doubt. They might say something about right angles, but they don't say anything about right triangles. Now, it's very awkward to figure out how to say this. Like, what's the reason why we know they're right triangles? Well, if you look up, and I actually did this for one of my classes once, if you look up on Google, right triangle, in their Google dictionary, it says a triangle with a right angle. It's built into the definition. That's the definition of right triangles. That's what it means to be a right triangle. So there we are with that definition again. And in case you're wondering, why do we keep using that definition piece over and over again? Well, instead of having to write out the entire definition of what it is we're trying to describe, when we say definition, it's just sort of the fastest way to get the job done. So, do we have a hypotenuse that matches? Yes, we do. Do we have a shared leg in common? Yes, we do. Do we have proof that these are right angles and therefore right triangles? Yes, we do. Which means we can cut to the chase, we can finish this proof off, and we can call it the HL theorem. So it's tedious. You have to go step by step, and it feels like it takes forever. How do I know it's a right triangle? Because it has a right angle. How do I know that it has a right angle? Because these were perpendicular. You're trying to follow your train of thought all the way from the start to the finish. I think you probably could identify the first three steps pretty easily. I think maybe even the fourth. And I know you definitely can identify the last one. These two in the middle are going to be the ones that are going to take a little extra practice. So the proofs are going to look a lot like this. We will use HL theorem in a proof here and there, and you're expected to be ready for it. Thanks for listening, and I'll see you next time.